Hi everybody, this is Mrs. Harding. You should have this handout from the substitute teacher. This is the last topic that we're going to cover for section 4.4. It's on writing limit statements for rational functions. So we'll do this today. You'll have a short homework assignment, and then Monday we'll do review, Tuesday is your quest. So let's take a look at this problem at the top that you were going to do with your partner. But it says below is the graph of the function x over x minus 2. So I've given you the graph there. The asymptotes are marked. There's a vertical asymptote here at x equals 2. There's a horizontal asymptote at y equals 1. And it says use this graph to determine the answer to each limit statement. So remember what this means right here. The limit of f of x as x goes to infinity. Oh, it's getting big fast. There we go. So as x gets very, very large, what is happening to the output values of the function? So this is going to bring us back to that horizontal asymptote. Remember how I keep saying the horizontal asymptote is about what's happening on the ends. It's about the end behavior of the function. And as x gets bigger and bigger and bigger, so if you're tracing this, all of the y values for these points are getting closer and closer to that horizontal asymptote, which is at y equals 1. All of those y values are getting closer and closer to 1. So the limit as x goes to infinity of f of x is equal to 1. And then the second one, the limit as x goes to negative infinity of f of x. Well, actually the same thing happens. Remember, the horizontal asymptote is the end behavior of both ends. It's just that the graph is approaching that horizontal asymptote from the bottom instead of from the top. So if we go towards negative infinity, that means my x values are getting more and more negative. I'm heading in this direction. What's happening to the y values on the graph? They're getting closer and closer to 1. So the limit as x goes to infinity of f of x is equal to 1. As it goes to negative infinity, it's also 1 because 1 is the horizontal asymptote. So the end behavior of any function, of these rational functions, is just the horizontal asymptote. That was the whole purpose for figuring that out. So 1 is the answer to those limits. Now there's also some strange behavior for rational functions because of these vertical asymptotes. So we are also going to write some limit statements for that. So you can see in this next section, limits can also be used to describe the behavior of the rational function near a vertical asymptote. Look again at the graph above. How are the y values changing as the graph gets closer to the vertical asymptote at x equals 2? All right, well, we've talked about this, that the graph either goes up or goes down directly next to a vertical asymptote. So really, what is the graph doing? Well, it depends. Which side are you looking at? Are you looking at the right side or are you looking at the left side? So we have to have some notation to explain that. So if you look at these two right here, this first question says the limit of f of x as x approaches 2, that little plus sign right there means from the right or from the positive numbers. So you're pretty much just looking at the right side, and as you're getting closer to the vertical asymptote, those y values are getting infinitely large, right? If I'm tracing this, let me get rid of these arrows that I had in here before. If I'm tracing this, getting closer from the right side, the y values are just getting bigger and bigger and bigger and bigger and bigger, infinitely bigger. So the limit as x approaches 2 from the right is infinity. So then, clearly this one is going to be from the left, and that's what that negative sign means. That negative sign, the way that you read this, is the limit of f of x as x approaches 2 from the left. So let's go back to the graph. If I'm approaching that vertical asymptote, but now I'm approaching it from the left. Well, now I'm here getting closer and closer, and you can see what's happening to the y values. They're getting infinitely smaller down here into the negative numbers. And so that's why the limit of f of x as x approaches from the left is negative infinity. All right, let's take a look at a different example. This is the graph of 3 over x plus 5. You certainly know where the asymptotes are, even if I didn't give you the graph. There's a vertical asymptote at x equals negative 5. So you can see that we have some limits written as x approaches negative 5 from the right, as x approaches negative 5 from the left. Also, there's a horizontal asymptote at 0, which is our end behavior. So if I needed to fill in these answers right here, the limit of g of x as x approaches infinity, that's talking about what's happening at the right end of this graph. Well, the right end, the end behavior of the graph is that all the y values are getting closer and closer to 0. Same thing happens on the left end. The limit of g of x as x approaches negative infinity. As you are going off, getting more and more negative, you are again approaching the horizontal asymptote because that's the end behavior of the graph. Now here, the limit of g of x as x approaches negative 5 from the right side. Okay, here's negative 5, the right side. As I'm coming in from the right side, these y values are getting infinitely large. So the answer to this limit is infinity. The limit of g of x as x approaches negative 5 from the left side. So now we're over here on the left and we're getting closer to the horizontal asymptote. Those y values are getting infinitely small. So the limit here is going to be negative infinity. Now on the back side, we're going to do 2 problems beginning to end. All right, question number 1. Determine all the needed information, make a sketch, and then answer the limit questions. Always your first step here is to factor anything that can be factored. And in the bottom, this is x plus 3, x minus 1. Now you have learned about removable discontinuities now, but this one cannot be reduced at all. So we know that x cannot equal negative 3 or positive 1. We can't reduce the function, so both of those are vertical asymptotes. Put those on the graph. Bear with me while I put these on. The horizontal asymptote, well, the degree of the top is smaller, so this is y equals 0. X-intercept, what makes the numerator equal to 0 is negative 1. And the y-intercept, what do you get when you put 0 in for x? You get negative 1/3. Let's put all those in here. So horizontal asymptote, x-intercept, y-intercept. All right, I know this guy's pointing down. I don't really know much else. I don't know if this side here in the middle is going to go up or if that's going to point down. So I actually need to find a few points on this. Let's see, I'm going to plug in negative 2. When x is negative 2, you have negative 1 over 1 times negative 3. That's going to be a positive number. It's going to be 1/3. So negative 2 1/3 up here, well, there's no more x-intercepts. So it's not like this is going to come back down again. It's going to go like this. And that's one of the first times we've seen a shape in the middle that looks like that. But I still don't really know what to do on either side of the asymptote, so I'm going to go 1 integer greater than the right side asymptote, so I'm going to put a positive 2 in here. So what is that? 3 over 5 times 1, so 2 3/5. Okay, so it's got to point up because there's no more vertical asymptotes. It's got to get closer to the x-axis because of the end behavior, the horizontal asymptote. And then I'm also going to plug in -4. When I put in -4, I have -3 over -1 times -5, which is going to be -3/5. So -4, -3/5. It's got to point down because I can't cross the x-axis and get closer to the horizontal asymptote at the end. So that's a different shape that we haven't seen before. Let's answer some limits about this. So first of all, the end behavior limits, these right here, when x goes to infinity and x goes to -infinity, that's just the horizontal asymptote. That was the whole point of the horizontal asymptote. So I can just drop zeros right into those. Now looking at each of these, oops, looks like I wrote 2's there instead of 3's. Let me change that in a second here. So limit as x approaches 1 from the right. 1 from the right side is here. That's going up to infinity. So the answer to this is infinity. The limit of f of x as x approaches -1 from the left, well, this is the asymptote immediately next to it as you're approaching. That arrow is pointing down. This one is going to -infinity. All right, make sure that you make this change on your paper. I'm not sure how that happened, but this should be -3 from the right, not -2, and this should be -3 from the left. All right, so the limit of f of x as x approaches -3 from the right, -3 is over here, getting closer to it from the right side, it's pointing up, that is going to infinity. If we look at it as you approach -3 from the left, that's here, getting closer and closer, it's pointing down, this one is going to be -infinity. All right, the last question. First of all, we need to factor everything. So this is going to be x minus 5 times x minus 1 over x minus 5, x plus 2. This one can be reduced. I'm going to take those 5's out. I'm sorry, I'm actually going to take a step backwards. I'm going to write down before I cancel it that x cannot be equal to 5 or -2. Now I'm going to reduce it, and the reduced function of x is x minus 1 over x plus 2. All right, so let's figure out if these discontinuities are asymptotes or holes in the graph. So if I plug 5 into this, it is not a problem anymore. Oops, I have a spot here for my removable discontinuity. So when I put 5 in there, I actually get 4 over 7. So that means there is a hole in the graph at 5, 4 over 7. When I plug -2 into the reduced function, it still is a problem. So this is a vertical asymptote at x equals -2. All right, horizontal asymptote, they are exactly the same degree. So I'm going to look at leading coefficients, 1 over 1. So horizontal asymptote at 1. X-intercept, what makes the numerator up here equal to 0? A 1 does. So 1, 0 is an x-intercept. The y-intercept, plug in 0, that is 0, -1/2. And I'm so sorry, I actually put a closed-in circle there for that hole in the graph, and I should not have. This should be an open circle at 5, 4/7. Please take a minute to make that change. All right, here I know what to do. This is going to get closer to the horizontal asymptote. This has got to point down because we don't have any more x-intercepts. I only need to put in probably one number to the left of that vertical asymptote. So I'm going to put in -3, which is -4 over -1. So -3, 1, 2, 3, 4. I know this points up, can't cross the x-axis, and then this has to get closer to the horizontal asymptote. So you have a full picture of the graph. So then the last piece is to write the limit statements for it. The end behavior limits are going to go towards the horizontal asymptote. These are both 1. It's getting closer to 1 as x gets very large and as x gets very negative. The other ones are for that horizontal asymptote. If I approach -2 from the right side, this is the right side, as I'm getting closer and closer from the right side, it's getting more and more negative. So these y values are getting closer to -infinity. As I approach -2 from the left side, well, that's over here, those are getting bigger and bigger and bigger. Those are going up to +infinity. All right, that question was a nice wrap up of all the things we've done here in section 4.4. I'll be back on Monday, so if you have any questions, you can ask me then. Enjoy the rest of your day.